Julie kindly asked me to conclude, well, together with Homeopathy, and she said from the past to the future, which was a very kind way to remind me of my age. So the first thing I'd like to, we've heard a lot about today, is that most of sickle cell anemia is in Africa. And I like to thank Dr. Dekile because many years ago, he made what I think was the first fine map showing the variation in frequency and the heterogeneity, which then turned out to correspond to the different haplotypes that we heard about from Sienna. So subsequently, largely thanks to the work of our moderator of today, and to whom I'd like to pay tribute, much finer mapping has been carried out, including in Tanzania. And my obsession for many, many years, since I took this picture with the permission of the patients and their mother, many years ago in Ibadan, Nigeria, why I'm showing you this picture is because this girl is AS and this girl is SS. So you might say, what is so special about this picture? Well, what is special is that these two girls are twins. And this was for me a tremendous message of the major impact that sickle cell anemia has not only on all the hematological features that we know, but also on somatic development. And so the issue that we have at stake is how can we convert this one into this one? So I thought that there must be a way to do it, but many people thought that, but somebody jumped the gun. And because I'm an old man, I want to remind you of this episode, which happened exactly 40 years ago. Doctor tried gene therapy on 2 humans. I will not bore you with the details. They were involved one distinguished hematologist from Los Angeles, one from Naples, and one from Jerusalem. And 2 patients with severe beta thalassemia got radiation, and then they were injected with a plasmid that contained the beta globin cDNA. Now, you might say with hindsight, we could tell that it couldn't work. As a matter of fact, no, we already knew then that it couldn't work because we need genetic engineering. And I realized that genetic engineering was actually going to work when it got into children cartoons, because they know very well what is of interest and what is technologically powerful. So already many years ago, it was fairly obvious that we could, if we do it in the right way, insert a gene into a cell and get that gene to express. And in fact, as early as 1982, it was fairly easy. At that point, we wanted to treat diseases, but many of the responsible genes were not yet even known. So the idea was clone the gene, insert in a vector, transfer into hematopoietic stem cells, obtain appropriate expression in progeny of stem cells. And when I was in New York, I was lucky to recruit to the Sloan Kettering Michel Sedlan, and he had produced hundreds of globin vectors. And in the end, he found that the best of all was TNS9. And we did this experiment in mice. This is a normal mouse. This is a thalassemia mouse. And these are 2 mice that were corrected by gene therapy. Here you can see the high level of expression of human hemoglobin in the mouse. Well, actually, it is a alpha mouse, beta human hemoglobin. And this was in year 2000. And John Tisdale has just told us that now it can be done in humans. And this was the first patient so treated. Dr. Makani has already shown us this. What I'd like to emphasize is that this patient was treated with exactly the same vector that John told us. And here is his hemoglobin A and his hemoglobin S. And it means that his total hemoglobin is now normal. And he is still, of course, making hemoglobin S from the endogenous genes. And hemoglobin A with that very special change, which is from the inserted transfected lentiviral transplant gene. So this is a fantastic achievement that we were waiting for. And here I've tried, because the question of allogeneic hematopoietic stem cell transplantation versus gene therapy always comes up. And I've tried to indicate in a very, forgive me for being so crude, I've only highlighted some important aspects. So both need some degree of myeloablation, mild to heavy. If it's successful with transplant, you have converted the patient who is SS with donor cells. The donor will usually be AA, but very often it may be a CIP who is actually AS. And this is the ideal. In the case of gene therapy, you've converted SS cells to AS cells because the endogenous genes will still make S, but the transfer gene will make A or whatever modification of A. But what often happens with transplant is you get mixed donor chimerism, meaning that there is only a component, but there is some resurgence of the endogenous hematopoiesis and erythropoiesis. So one very interesting thing that I can see is that are we getting a real phenocopy of an AS heterozygote? And the answer is, with transplant, no. Getting usually chimerism, so AA cells and or AS cells and SS cells. But with gene therapy, you potentially get expression of A and S from every cell, and therefore it is a true phenocopy of an AS heterozygote. And of course, a monumental difference, which we sometimes we sweep under the carpet, but is very important, is the problem of GVHD. And from this point of view, as has been stated by some speakers before, it could well be that gene therapy is not necessarily more demanding than transplantation. So the new dimension that I actually never expected was that there was a third possibility. In addition to gene addition, many years ago, I thought of gene replacement by homologous recombination, which I called the labor of love. But what I did not expect, because it only came later, was the possibility of gene editing. So I've added emoticons with different amounts of smile for these different alternatives. And of course, gene transfer and gene editing are very similar, but they're not exactly the same. So in the case of successful out of gene transfer, as I've already said, you make an AS from an SS. But in a gene editing, usually it will be probably similar, because it's unlikely that you're going to convert both alleles in the same cell. But it's possible. And some of the results we saw today from Matt, I think, suggest that this is happening because you get more than 50% of hemoglobin A. So I think that the question of mosaicism still remains to be seen. And therefore, I'm very enthusiastic about this possibility. And since I was asked to tell you about the future, I don't have the crystal ball, so I I can't tell you what will happen, but I can tell you what I hope for. So what I hope for is that this becomes that. And the future is wishing successful gene therapy of sickle cell disease at Muhimbili and sharing with you the enthusiasm for June 19, Juneteenth. And finally, because there are donors who can help us, can I remind you that we still need hydroxyurea? Thank you very much.